In this video, I discuss how to determine the Gaussian dispersion coefficients, that is horizontal dispersion coefficient and vertical dispersion coefficient. But at first, we just recap what is the Gaussian plume equation. Suppose a stack with height small h releasing pollutants into air at a constant rate q. The effective stack height is capital H, that is the original stack height plus plume rise. The average wind speed at a effective stack height is UH if the horizontal dispersion coefficient and vertical dispersion coefficient of pollutants are sigma y and sigma z respectively. The concentration at a given point can be determined by using the following Gaussian plume equation, where C x y z is the concentration at a given point. X is the distance directly downwind, y is equal to crosswind horizontal distance, and vertical distance is z. Now, how to determine this UH, that is average wind speed at effective stack height, is discussed in my last video. So we just recap this very quickly. Usually wind speed is measured at an anemometer height of 10 meter above the ground. So a relation of wind speed at the anemometer height with wind speed at the effective stack height UH is expressed as UH by UA is equal to capital H by ZA to the power P whole to the power P, where the UA is the average wind speed as recorded by an anemometer, H is the effective height of the plume, ZA is the anemometer height above the ground, generally it is 10 meter, and UH we have to calculate the wind speed at elevation H, and P is the profile exponent wind profile exponent. So according to the recommendation of US EPA, the value of P for a rough terrain in the vicinity of anemometer is depend on stability class A, that is very unstable, B is moderately unstable, C is slightly unstable, D neutral, E is slightly stable, and F stable. And value of P is accordingly 0.15, 0.15, 0.2, 0.225, 0.4, and zero point 0.6 respectively. And for smooth terrain such as flat fields or near water bodies, this value should be multiplied by approximately 0.6. Now, basically, we start today's topic. The dispersion coefficients sigma y and sigma z are just the standard deviations of the horizontal and vertical Gaussian distribution respectively. Smaller values of dispersion coefficient mean the Gaussian curve is narrower with higher peak, and larger value means the opposite. This is some of the Gaussian plume curve. You can see that this is very taller, higher peak, and with narrower. So here the value of dispersion coefficient is less, that is 0.5, you can see here. And for this violet color curve, that it is wider, and is the value of the Gaussian dispersion coefficient is maximum of these three curve. So it is very wider. So the empirical rules states that about 68% of the area under Gaussian curve is within plus minus sigma, that is within plus minus standard deviation of the mean. 80% lies within plus minus 2 sigma of the mean, and 99.7% lies within plus minus 3 sigma of the mean. Now, these coefficients are not only a function of downwind distance, but they also depend in a complex way on atmospheric stability. And the basic equation for obtaining sigma y is equal to a into x to the power 0.894, and sigma z is equals to c into x to the power d plus f, where a, c, d and f are constant. And the value of these constants depend on each stability classification, that is a to f, that I discussed in my next slide. So the values of this constant for each stability classification is here. You can see that the A is fixed, the value is fixed, but there is two sets of C, D, E, C, D and F is found. One is for when x is less than or equals to 1 kilometer, or one is x is greater than 1 kilometer. So here you can just remember that the downwind distance x must be expressed in kilometers to yield sigma y and sigma z in meters. So when I go through calculate some of the or examples, we have solved some of the examples, it will be clear. So for example, suppose carbon monoxide emission rate from vehicles from a given point on a highway is 0.021 gram per second meter. If wind is perpendicular to the highway and at blowing 2.2 meter per second on an overcast day, calculate the vertical dispersion coefficient sigma z at 10 meter from freeway. So the basic equation for obtaining vertical dispersion coefficient is sigma z is equal to c into x to the power d plus f, and as this is a workers day, so we should use stability class D here, and the value of C, D and F are taken from the from this table. But here we can see that we have to identify sigma z at 100 meter, that is 0.1 kilometer. That is, we have to use the value from this set of values, and by using this we can get, by using this formula where C is 33.2, D is 0.725 and F is -17. So I put this value here and accordingly get the vertical dispersion coefficient. So we go for another example. A coal-fired power plant in rural area emits sulfur dioxide from the stack with effective height of 90 meter. Wind speed at effective emission height is 7 meter per second. Weather is overcast. Then calculate both dispersion coefficient, dispersion parameters, that is sigma y and sigma z at 1.5 kilometer from the source. So the basic equation for sigma y, we know that it is a into x to the power 0.894, and sigma z is c into x to the power d plus f. So as this is overcast day, we should use stability class D, and here we remember that is x here is 1.5 kilometer, that is it is greater than 1 kilometer. So you use this set of values. So for calculation of sigma z, we use For A value is 68. X, it is 1.5. As you know that X should be in kilometer to get sigma, is to get the dispersion coefficient in meter. So we use this formula, and the sigma y is 97.71 meter, and in case of sigma z we use this value, and it is 41.86 meter. I think it is clear. For more reference you can read these documents. Thank you for watching this video.